And in true UIT fashion, it seems the wireless mic in this room will never be fixed. So you're going to have to listen to the beautiful sound of my screaming voice for the next hour and a half. Big congratulations to Pejman, who's actually getting his Canadian citizenship today, so yay. And today was kind of an open topic, so I'm going to be talking about applications of artificial intelligence in games user research. So without further ado, what are we going to be doing today? Well, I'm going to be giving kind of a brief cursory overview intro of AI in games user research. I know depending on your backgrounds, you'll have kind of a different level of familiarity with AI in general, since the AI course, unless the program has changed drastically, still doesn't happen until 4th year, which is actually a shame. We're going to talk about some different applications, kind of two main categories, the first being data analysis, the second being playtesting. Now, to my knowledge, these topics related to AI aren't going to be on the midterm, so don't stress yourself out thinking that you're going to need to know the ins and outs of different AI applications, blah, blah, blah. This is more just for kind of research interest. Those of you interested in research or grad studies might find this lecture particularly interesting. And just kind of for your own knowledge, kind of what are the frontiers of games user research, what's happening. We're going to be talking about some of the challenges of working with AI in games user research more broadly. You know, how do you evaluate these new systems? How do you prove they're doing what they're supposed to be doing if you're not even exactly sure what the outcomes are that you're going for from the start? And we're also going to have a presentation from Jason after the lecture. Yes?
Sorry, I have to move it.
Oh, okay. Well, in that case, we'll have your presentation on Wednesday, Friday. I'll check the schedule. Later, okay. So, before we get started, well, what is artificial intelligence? And I'm sure everyone kind of has their own idea of what artificial intelligence is. There's a lot of different definitions, but the general research consensus is, unfortunately, that there is no research consensus. There's really no kind of universal agreed upon definition for AI. There's no textbook definition as such. You will find a lot of different definitions in different materials, but ultimately the definition of AI kind of varies between different domains where it's being applied and so on. So very broadly, you can think about artificial intelligence as the ability of a computer to acquire and apply knowledge and skills to solve problems. Essentially, the kind of holy grail of AI, that is general AI, is the ability of a computer to acquire knowledge and skills in the same way that a human might, so that it might be applied to solve any kind of problem, having never been exposed to that problem before. And that's really kind of what AI research is all about. It's creating these models that generalize to never before seen situations so that you can approach problems with a system that learns from experience, essentially. So there's kind of multiple different types of AI. You'll see classical AI or expert systems, and these are systems that are kind of programmed by hand. So even though they're not explicitly programmed to solve every instance of every problem that they're meant to solve, there's still kind of hand-coded instructions in there. And a lot of game AI uses this kind of a system. So if you've heard of something called a behavior tree, where basically a human programmer specifies a decision at various points, you know, if the player is close to you and you're an enemy, then attack. If the player is close to you and you're an ally, then heal. That sort of thing is classified as classic AI or an expert system, since there's still ultimately a human coder writing explicit rules for the system to follow. Now, more recently, what the kind of buzz has been about, and what some of you may be familiar with as well, is machine learning. You kind of hear this used as a buzzword all the time, machine learning, deep learning, neural networks, but machine learning as a catch-all term is just kind of used when you have an AI system that solves a problem without being explicitly programmed to do so. So the most common example of this that you can probably think of is a neural network. Essentially, this is when you build a model of your data. It's purely mathematical, and the system kind of trains itself over time. So the way a neural network actually works, for those of you that are interested, is you have some set of outputs that you're turning into some set of inputs that you're turning into some set of outputs. So maybe you're taking a bunch of images and trying to tell whether they're cats or dogs. Those inputs go into a network that essentially takes the pixel values in each image, say, multiplies them by a bunch of values, adds them all up, mathematical mumbo jumbo, and spits out a label that says cat or dog. Now, that mathematical mumbo jumbo part you'll be learning about next year, but what you really need to know just to understand why machine learning itself is so powerful is that the parameters of those mathematical operations, essentially what the computer's doing, what weight it's giving to each of those operations, is learned over time. So the machine learning algorithms basically train themselves given some ground truth output to reproduce that and then generalize to other types of problems. So if you show the network an image it's never seen before, it'll still be able to classify it even though it's completely new information. So that's really kind of the power of deep learning, and it's often called the second best solution to everything, since these kinds of systems can work on any problem in theory, but are usually slightly worse than a handcrafted approach. Now, thankfully, that's starting to become an exception these days because quite a few domains, image generation, for example, other automated approaches really can't touch what neural networks are doing in a lot of domains. But nonetheless, the axiom holds true that this isn't a blanket solution to absolutely everything, at least not just yet. So where does this come into games user research now that we have a very basic understanding of what AI is, what machine learning is, and so on? Well, the first thing we're going to talk about is AI for data analysis. Now, why would we want to use AI when we're looking at something like analyzing playtesting data? Well, there's challenges inherent to the data analysis process that can make it really difficult for humans. First off, data can be nebulous. What do I mean by that? Difficult to interpret. So if you're looking at a chart of numbers from a questionnaire filled out by 200 people, even if you know all your descriptive statistics and you're looking at the broader patterns, it can still be really difficult to read in what it is you're trying to find out. Imagine you're trying to infer how players feel based on their questionnaire responses. Where do you even start with that? Some things, like emotion, are hard or impossible to kind of measure. So what you really need to do is take related measurements, for example, someone's facial expression, their vital signs, and so on, and then try to infer it based on that data. Second, data can be voluminous. What do I mean by this? There can be a lot of data. When you have playtesting videos from thousands of players taken remotely, or you're a, say, AAA publisher and you have metric data taken from thousands and thousands of players, you have huge quantities of data that's basically impractical or impossible for a human to sift through. It's very labor intensive. You have to pay a lot of people. And even in doing so, there's no guarantee that they'll be able to interpret that data effectively and that they'll be able to get it done in a reasonable amount of time. So how can we use AI to help us solve these challenges in particular? That's what we're going to be looking at for around the next 15 minutes or so. But before we get started, does anyone have any ideas about how you might use AI or some other form of automated approach to kind of tackle those challenges with data analysis?
What do you mean by that?
Like, how do you think you might, what tasks in analysis might you want to automate? And then do you think that you'd be able to use machine learning? Do you think that you'd kind of be able to program an expert algorithm to sift through the data? Like, what are some applications that you might see? Maybe what are some pain points that you faced in testing and analysis yourself that you'd want to automate? Yeah.
You can have it set up everything properly in an Excel sheet really quickly, better than slides would do on its own, or Google Forms would do on its own. You could also set it up to find correlation graphs between certain numbers and each other.
Right, yeah, so that's an example of what an expert kind of system or a script might do. You could use that to kind of automatically process your data, finding correlations automatically through AI, kind of determining which pairs of variables are correlated with each other, or kind of which data points the researcher might want to look at further is actually something we're going to be talking about in here as well. So yeah, good points. Anybody else? Okay, so moving on. There's a few different categories we're going to look at. Sorry, what was your name?
Josh.
One that Josh just kind of hinted to was assisted data analysis. So there's a whole field called data visualization. Chris Collins actually teaches a course on it. Hopefully he's teaching it this year. Highly recommended. Yes?
Sorry, another one, potential suggestion.
Yeah, for sure.
What if there was like an AI that it knows what it wants the death rate in the level to be, for example, and then it adjusts maybe like player damage or something, or enemy damage or something to basically iron out death rates as it sees fit through balancing.
Yeah, that's actually a really interesting point. We're going to be talking about something similar to that in the second half of the lecture on AI for testing, so hold that thought. You kind of hit the nail on the head there. So the field of data visualization and kind of data processing in general, more and more programs are being developed which have some form of kind of intelligent assistance. So what this might mean is that you're inferring user goals based on sequences of actions. So if you notice the user using basic pattern recognition and sequence recognition techniques tends to, call a chart on a pair of variables, check the correlation coefficients, and then export the data to a screenshot that they then save into a spreadsheet, and that's kind of their workflow. As that algorithm or that program learns to recognize different sequences of user action, after the user's taken a couple of actions from that sequence, the program can then suggest in the form of a tooltip, it looks like you're just doing what you just tried to do based on your workflow. Would you like me to automate the rest of this so that your kind of analysis process can be faster, which is, I think, part of what Josh was alluding to, just kind of speeding up that whole process. And there's programs now that you can do this without having to explicitly code in, we assume that people are going to take this series of actions. That's not what this kind of intelligent assistant does. It actually learns from the individual user. So it'll kind of mine patterns of action from the individual user to tailor the experience to a particular analyst rather than relying on, say, a library of patterns of actions built up by a developer. You can display kind of relevant tooltips. You can suggest maybe filters on your data. You just looked at all female players. Do you now just want to look at all male players? You just separated players by experience level. Maybe do you want to separate them by age as well? And this is kind of done by learning online from the user's actions. You can also highlight individual data points to try and help with the task of analysis at a higher level. So a couple different ways you might do this are to highlight points that are relevant to the current task. So if you detect that your analyst is looking at, say, all the playtesters that completed the test in a given week, you can kind of automatically highlight the rest of those data points. Another interesting one, which actually, as I said, Chris Collins, who works here in data visualization at the school, has talked about before, is something about kind of automatically determining which data points might be perceptually difficult to identify as relevant, but are still relevant for, say, trend analysis or outliers or something like that. The idea there is that a program would essentially kind of gauge the analyst's level of perception, whether you'd notice that a particular player was mathematically an outlier for a given metric, for example, and then it would highlight those points that are maybe not so obvious, but that are still mathematically significant. So one kind of really maybe obvious, if you know AI and you know games user research, application of AI for data analysis is emotion recognition. I know a couple people have already done / are planning to do their presentations on the challenge of emotion recognition and kind of psychological analysis in particular. What the heck? I think that's a bit unusual. I don't know what just happened. Yeah, apparently. Sorry about that, guys. So some of the challenges of emotion recognition mostly relate to that point I made earlier about the data being nebulous. It's very difficult for a human being to say, look at a gameplay video and then annotate at each and every moment what a user was feeling. And likewise, when you go back and maybe ask someone in an interview, how were you feeling in this exact moment? They're subject to their own internal biases. Human recall is far from perfect. So this is one of those tasks where AI can really help us with the analysis process. And what you can do here is you can consider multiple different data sources. So not just, say, facial recognition for whether someone has an angry expression or a happy expression, things like gestural recognition, body movement. These are all things that computer vision, kind of the subdomain of AI related to image processing and kind of inferring information from visuals, has been working on for a long time, both for things like emotion recognition and for, novel interfaces where you want to gesture at your computer to get it to do something. Speech and voice processing. Based on the timbre of someone's voice, you can also kind of make conclusions about whether they might be nervous, angry, satisfied with their experience, and so on. Another thing is sentiment analysis. So this is when you're essentially taking text or language and you're parsing it to determine what the sentiment behind that was. So if someone exclaims during gameplay, "I hate this game, it's terrible," sentiment analysis would reveal that they're displeased or angry. Likewise, if they say, "I love this game, it's fantastic," it would infer that they're happy and satisfied with their experience. And you can do this on all kinds of different data. So not just say how the players look while they're playing, but maybe the text of their interview responses afterwards. And the beauty of AI and machine learning algorithms in particular is that you can kind of feed in data from all these disparate sources as different features, and it will consider all of that in kind of making its conclusion. So if you have, say, an emotion classifier machine learning algorithm, you can input all of this data as features to it rather than just considering one data source at a time. And as a human, this intuitively makes sense, because if you're interacting with another human, when you're trying to figure out how they're responding to you in conversation, you're not just looking at their face or just listening to their voice. You're kind of considering all the data you have about them. And that's kind of part of the reason why machine learning algorithms are so powerful and have become so popular, because they can recombine data from so many sources to make judgments. Not saying that this is a perfect solution, far from it. Machine learning algorithms are still in their infancy, in all honesty, in modern times, and we've got a long way to go. But this right now is still kind of our best shot at identifying how people are feeling without actually having to rely on asking them directly, relying on the human powers of recall and so forth. So another interesting application of AI and data analysis is something called player modeling. And this is trying to understand user actions kind of based on broad categories of players and based on the characteristics of those players. You might be familiar with some of the kind of precedent for player modeling, which is referred to as typology. So if you guys have seen kind of the Bartle types or Brain Hex or any of those other gamer typology quizzes where you're essentially trying to bin players based on their actions, these are all handcrafted. So essentially researchers, psychologists, experts on game design come up with these categories of players and then bin players into them based on actions. Now, player modeling, on the other hand, is kind of the computational approach to this. So it's trying to take data from players, a data-first approach, and then create categories based on that data. So let's say you have metrics from 1,000 players, and you want to group players based on what they're doing. Maybe you see there's a lot of players that don't use combat very much and also don't die very much, so you classify them as pacifists. And then there's players that maybe die all the time. They're always taking out their weapons. They're burning through a lot of resources, and you classify them as aggressive. Now, there's different kind of levels of automation in this. One of the ones that we're going to be really interested in actually uses machine learning, but the way this is generally done is to employ some form of AI or basic statistical processing. So you'll basically calculate descriptive statistics on kind of every measure you have, and then try to identify parts of the distribution that are clustered, and then those clusters form your categories of players, your kind of player model. So machine learning has been used for this. There's a couple of interesting papers about this. If any of you guys are interested about that, kind of feel free to send me a note and I can send those papers along your way. They're all based on clustering algorithms. So in machine learning, clustering is what's called unsupervised. You basically feed the data into the algorithm, no ground truth. You're not telling it what you expect, and you just try to extract those clusters from it. So what the algorithm will do is it'll essentially plot everything based on every measure it has, and then try to identify those groups that are really close together on different measures. There's a lot of different ways of doing this, but the end goal of that is basically identifying groups. So your input here is your feature data for individual players. Maybe for every player you have the time they take to complete each level, the number of times they died, how they died, and so on. That's kind of your input to the algorithm. And your output is clusters representing similar play styles for the different players. This helps you kind of understand the distribution of behavior among your players. It might help you to identify better who your players are and how they play. And as a developer, why you might find this information interesting is that it can kind of guide your future development, maybe where the next installment in a franchise should go or what kind of DLC you should be developing. You know, if you've just created a Tomb Raider game and you're finding most of your players are focused on puzzle solving and they're kind of avoiding combat with enemies, maybe that tells you either you need to improve your enemy AI or your core player base is simply more exploratory and focused on the puzzle solving that you thought. Maybe that's an indicator of where you could push the franchise or the kind of DLC that you could create to keep your current player base happy. It helps you really then to kind of better understand your target market. maybe the players, the intended experience you thought is only had by a small fraction of your player base, and something you didn't really anticipate is identified as this huge cluster of players, this part of your target market that you really had no idea existed, that you weren't sure how to deal with. And that kind of new information can just be really helpful to a developer. You can see why, as a human, it might be really difficult to perform this kind of analysis task. You know, if you have thousands or even millions of players, all these different metrics that essentially get plotted into higher dimensional space, as a human analyst, you really have no idea what you're looking for. And that's where these kind of clustering algorithms from machine learning come in. Another kind of model within data analysis is the idea of behavioral prediction. So based on players' past actions, what are they going to do? How can you extrapolate based on kind of known history of actions? You can learn from multiple players. You can learn from data from an individual player. There's quite a few different ways to do this. Ideally, though, you need lots of data. So this probably isn't something you're going to be able to employ doing, you know, a guerrilla play test with 6 people. This is, again, an application that's more commonly used in the commercial space, or if you're a really successful indie game and you have metrics coming in from hundreds or thousands of players. There's a few different ways to do this. This is going to look a little scary for those of you that haven't seen AI kind of deep learning techniques before. There's a specific type of neural network that if you're interested in deep learning, I recommend you look into, called long short-term memory networks. And these are used for tasks called sequence prediction. So an application of this in the hard science is something like maybe weather forecasting or economics forecasting. In games user research, if we're doing a sequence prediction task, the sequence that we're predicting is, say, a series of player actions. So the input to that, if you're playing a strategy game, might be the player purchased this unit, then they put another unit over here, then they killed their opponent's, like, I don't know, production facility or what have you, whatever your library of actions is. And then your long short-term memory network essentially takes that series of actions as input and outputs a prediction for what the player is going to do next. And that prediction is either based on the history of actions from that individual player or kind of the library of action patterns you have from all players. So in this way, you can kind of see how this strategy can be used to identify kind of high-level player strategies or common threads of experience. If you see a lot of players in your game go through the same sequence of killing a particular enemy, finishing a particular quest, buying a particular item, and then starting another quest, chances are that your network, if given the fact that a player just killed that enemy and bought that weapon, they're soon going to be finishing that quest. Or, you know, what have you. This can really be applied to any broad pattern. And you can see here the power of machine learning to generalize. This is why these algorithms are so powerful, are so popular. Because this particular method isn't specific to any type of game, any genre, any particular title. All it needs is really a library of actions for any given game, and then you can kind of apply that to try and predict player behavior. Another technique for this that's related is called pattern mining. So essentially, if you have data from a ton of players, the algorithm goes in, tries to identify snippets of actions that happen over and over again, and then kind of use those to train a model that will then predict based on those little snippets that a ton of different players tend to go through. So one application of this is goal recognition. So this is kind of trying to infer what a player's high-level objectives are based on low-level actions. In an RPG, this might be using kind of which enemies have been killed and which items have been purchased to try and determine which quest a player is thinking about completing. In a strategy game, it might be what types of units they're buying or what types of combat actions they're taking to try and determine whether they're taking a defensive strategy, a really offensive strategy, and so forth. So these are the kinds of questions that you might be aiming to answer with the goal recognition task. And you might be wondering, you know, why is this useful? Why not just watch players and see what they do afterwards? I'm testing the game. I don't really care. And my answer to that is, you know, if you're, yes, go ahead.
Let's say they're playing Skyrim, right? And
yeah.
They want to see like what kind of quests they want to do. Would you want to give the player a couple days to play the game rather than like one long session? Because there might be some sort of bias or some sort of like inclination where like they just kind of want to push to finish the story or whatnot. How do you go about like just doing like RPGs that are really story quests heavy?
Right, yeah, so that's actually a really good question. And it kind of brings up the idea of almost ecological validity with respect to, say, training. So let's say you're training one of these algorithms to recognize what players' goals are because you just want to improve the maybe quest manager in the game. So as you said, if you're training these based on really short play sessions, players might be biased to just try and power through as fast as possible because they know their play time is limited. If you're training a model like this for a live game that you're actually trying to improve online, as you said, it's much better to collect data from players remotely, that they're playing in their own home, playing at their own pace, because that's more reflective of the actual data you'll be getting from players in the field. Now, if you're doing this just as part of a playtest for whatever reason, maybe you have a limited amount of testing time and you want to try to extrapolate what players would do if they play for another hour, but you only have time to test them for an hour, then it would be sufficient to train the model for that hour, since the environment that you'd be testing them in for the second hour would still be that lab environment. But I hope this answers your question to an extent. When you're using these models kind of live to update and improve a game, you definitely want to maintain ecological validity in your training data as much as possible. So that's an excellent point, that you really should, wherever possible, be collecting these metrics from players playing in a natural environment at their own speed and the like. So what this is useful for, contextual help systems. If you can infer what goal a player is working on based on their actions, you can select hints that would be appropriate for them if they request help. So if they're playing an RPG that they have, 10 quests active, and maybe they're stumped on a puzzle from one, or they're not sure what they need to do next, but you don't want to have, say, a tips UI for every single individual quest. You want to declutter your UI, but you want to display to users information that's helpful for them. Maybe if they go talk to an NPC hoping to find out information about their current quest that they're focused on, you can intelligently determine what that quest is and provide that information contextually, increasing immersion, rather than relying on, pages of manuals and hints that are hand-authored for every quest that the player has to go in and pick out themselves. More believable in-game AI. So imagine, again, to go back to the example, you're doing this for a strategy game like StarCraft. If you can kind of infer what player's grander strategy is, you can maybe give an opponent that will automatically choose a strategy that counters the player's strategy to make that AI even more difficult to beat, to kind of make something more engaging. If you're playing against a human opponent and they figure out what your strategy is, they're going to try to counter it. A lot of classical game AI is really terrible at that sort of thing, and is part of the classical complaint about strategy game AI being terrible. So this kind of approach can be employed to kind of improve that. And this is also the sort of approach that you will see a lot of the kind of lower level, not quite inscrutable deep learning AIs that are trying to beat human players using as well. You can also use this to identify points of interest in gameplay. So if you see a lot of your players are kind of having the same overarching goals, if one strategy is kind of beating out another, but you don't have a ton of time to test your game, so you need to kind of infer that based on the data that you have. This can help you kind of gauge which strategies are maybe most popular, which subsystems players are engaging with the most, and so on, which as a developer, as a researcher, can be really helpful. So player retention and purchase behavior. This is, again, maybe the dark side for some of you if your attitudes towards mobile games and microtransactions or anything like our years was, but nonetheless, this is still kind of an interesting subfield of behavioral prediction in games. So retention is a term for how long players stick with a game. And there's been a little bit of research done into this using AI to try and predict where and when players will give up on a game. Obviously, as a user researcher, this is interesting to you because if you can pinpoint the time when players finally say, you know what, I'm bored with this game, or I'm too frustrated with it, I'm done, and hand that back to the developer, they can then identify maybe which content isn't engaging enough or where players are becoming too frustrated to continue. So you can then predict where players will kind of waver and maybe encourage them to stay with some kind of incentive or showing them some new content and so forth. So the way that you would do this is basically following that idea of taking a bunch of low-level actions to predict those high-level strategies. You can train an algorithm to kind of recognize patterns of action that ultimately lead to a player leaving or logging off and not logging back on, and then you can kind of recognize those points where that happens. And again, there's some papers on this that if anyone's interested, maybe I'll put them up in the Discord later. Okay, so purchases. This is another interesting one. Basically here, you might try to identify patterns between game actions and purchases. You know, if a player loses a competitive match in this mode and then they tend to buy an upgrade for this weapon, maybe we can say whenever a player loses a match in that mode over and over again, we put up a little prompt or maybe give them a special offer on that weapon, put it at the front of the store page, give it a slight discount, This verges on dark design since you're essentially trying to kind of manipulate player psychology and get your players to spend money by realizing the fact that most players will have caved and wanted to buy something by that point. But this is something that developers are doing. This is something that as a developer, if you're making a free-to-play game, would make you money. So I'm talking about it here anyways. Do with this information what you will. Please use your powers for good. But I'm not the police, so I can't tell you what to do. Another thing that you can train on for this, the type of data you can look at, is items that are purchased together. So if you notice players buy a particular weapon and a particular skin together, maybe you can offer your players a bundle that puts those two items together, increase the overall volume at which players are making that transaction, and ultimately, as the developer, end up with more money in your pocket. No, EA did not pay me to make this slide. You can also use this to drive kind of recommender systems for different items. Now, here, you might not even be doing this for, say, a storefront that actually uses currency, that you have microtransactions. You might actually use this in a game just to kind of push up those items which players find useful, to kind of maybe make your economy interface a bit more intelligent, to put what players care about up top so that they can get back into the game more quickly, and that sort of thing. So that's kind of the first half of the lecture wrapped up. We're going to look at AI for testing right now. If you guys have any questions, feel free to put up your hands whenever. But changing gears a bit, we're going to step back from just looking at the data and look at how we can use AI as part of our testing process. So some of the challenges related to game evaluation and testing in general, other than trying to hear your voice as a lecturer when there's people in the room that are talking to each other and you have really good hearing. Testing is both expensive and time-consuming. So the resource requirements for testing, it's not just that you have to pay a lot of money to hire more people for your user research team and that you have to compensate your participants, but as those of you who are frantically working to finish assignment 2 know, it's time-consuming as well. If it's the night before you want to deliver your results and you want to test with 8 players for an hour each, good luck. It's really difficult, and especially as an indie, when you have quick turnarounds and you want to be the best developer that you can be and do a lot of iterative development, but you really just don't have time to test with your players for 2-hour blocks every couple of weeks, it's a big challenge. Each iteration requires a lab space. It requires recruiting participants. Testing often happens over many days or many weeks, so it's really difficult to kind of get everything in one place and just finish it in a couple of days. Recruitment is really difficult. You need to coordinate schedules between your team and your participants. You need to find people that reflect your target audience, and it can be really difficult to find players in sufficient quantity that kind of reflect the target audience that you're looking for. So if you're making a game for kids, especially if you're working at a university, aside from taking your colleagues and going, please, please, will you bring in your toddlers to play my game, it can be really difficult to recruit from that particular audience. Maybe you're looking to recruit people that have very high experience in a specific MMO that you're building maybe a mod for. Really, really difficult. So how do you guys think that you might be able to apply AI to help kind of improve the efficiency and maybe even the quality of the testing process? Does anybody have any ideas? And Noah alluded to this a bit earlier with his response as well. Nobody. Okay, well, I'll assume and hope that you guys bring up some points during the discussion as we did before. Feel free to put in at any time. So there's kind of a few different categories of AI game evaluation that we're going to be looking at. The first is quality control. Yes, I know Pejman would lambaste me for saying the words quality control during a games user research lecture. I am well aware that quality control is not games user research per se. But the reality is that kind of applications of AI and testing in general, there's kind of a broad spectrum of methods that go from, quality control and kind of a dumb system that just looks for bugs and crashes to a system that tries to mimic players' experience at a human level and provide you some insights regarding user experience. So we're going to be talking about it anyway. Playability evaluation. Playability is basically referring to whether a game's content is kind of possible to complete, whether it's valid, whether it's balanced, these objective measures. So these, you'll be looking at AI systems that try to simulate play objectively. They try to play well, they follow the rules of the game, and you're just kind of looking for whether your content is valid. Now, the last category is kind of the most interesting one, to my mind at least, and this is trying to apply AI to provide some form of automation to user experience evaluation. So here you'll be looking at simulating human behavior or trying to simulate play subjectively or critique it. Here you'll be looking at AI agents that don't just follow the rules of the game and attempt to play well, but attempt to mimic the flaws in human behavior and the differences in individual players without sacrificing the fact that humans, generally speaking, still play games at a level much more proficient than a random computer system, even though that's changing with the likes of, DeepMind and AlphaGo and so forth. For your average automated AI agent used by a run-of-the-mill developer to find bugs, it's not going to be nearly as good as a human player. So that's where this really comes in handy, because you're kind of trying to make a term that I've heard before that I think is really appropriate here is artificial stupidity, something that plays in the same way that a human does while recognizing the flaws of a human player. So when we look at quality control, obligatory, yes, disclaimer, quality control is not games user research. But here we're looking at things like automated crash and bug detection. So if you have an AI agent that uses exhaustive search or random inputs to try and crash a game, see if you can find those weak points and identify the vulnerabilities in a game. Reporting any unintended behavior, so if you find an area of the map that players can, glitch out of. And all of this is just kind of aimed at replacing the human labor that you would traditionally have with quality assurance testers. You can also have these systems kind of output footage or crash logs that then is inspected by a human analyst. The idea here isn't that you're going to basically replace your quality control team with a bunch of robots. It's that you'll be able to kind of empower them to test more and test more quickly without having to sacrifice a ton of your resources to do so. So a couple of examples from the literature. You guys can look these up on Google Scholar if you're curious. I'm going to talk about Icarus and Cicero, and I really like the acronym on this. They did a good job. Anyway, Icarus was this system that was developed to test adventure games built with a particular engine, but the notion being that it was kind of, if you want to use the phrase Turing complete for that engine, that it could test absolutely any adventure game built with that platform for completeness, to make sure players couldn't get caught in an infinite loop, to make sure the content was playable, that there weren't any rendering glitches, that there weren't any crashes. And the way this worked was they kind of combined a few different agents. They tested one that just used random inputs, that took absolutely every possible action at every stage. And they tested one using something called reinforcement learning, which is a type of machine learning where you reward the system with some kind of score, some kind of information about the world state, rather than saying, this is the correct action I wanted you to take. You tell them what the consequences of those actions are. So if the AI, uses a series of items that gets them to complete a quest, you give it the computational equivalent of a carrot and say, good job, you just made your score go up a lot. And if they get rid of an item that was really valuable or that they needed to continue, you give them a penalty. You hit the AI with a stick and you say, no, bad. And over time, it learns what it needs to do in the scope of the game. That's kind of the Coles Notes version of reinforcement learning. So what they did was they tested all of these different agents, and lo and behold, they found that using a combination of reinforcement learning and starting out with kind of random inputs, they could get a performance in-game, time-wise, comparable to a human speedrunner that knew the ins and outs of every quest, that knew exactly what actions that it had to take at each time, starting from zero, which technically is quite a feat, that's very impressive. But kind of the more interesting part of this paper as a games user researcher is that the agents that they generated in conjunction with human analysts, they used to track down a lot of bugs in the game. So identifying infinite loops where there'd be some bad logic that the designers hadn't thought of with the different items that were included, maybe some locations where there were crashes or glitches with rendering and visual effects not showing up properly. The way they did this was essentially using the AI as a partner to that human analyst, where the human would be supervising what the AI was doing and analyzing it, rather than relying on a human tester who has to be playing and taking notes, for example, at the same time. And something similar that kind of viewed AI through the lens as an assistant to a researcher as well is this framework called Cicero. So Cicero is kind of a pseudo-general game AI that's built to play any game built with this kind of really simple arcade-style scripting language that you use to make games similar to, Space Invaders or maybe a Maze. This is kind of a proof of concept work more than anything else, whereas Icarus was actually applied in a commercial setting. So with Cicero, you have these agents that can play through any game that's specified in this language. What they did was they made a couple of simple arcade games in this language that intentionally had bugs planted. So errors in collision, things the player wasn't supposed to be able to do. Then they gave these copies of these games to testers. One of the testers one group of testers rather, had to play the game themselves and report on any of the bugs that they found. The other group of testers didn't play the game themselves, but it was instead allowed to watch these AI agents play through the games and then try to kind of detect the bugs based on that. Now you might be thinking that obviously a human knows how to enumerate the actions properly, so the people that could test the game themselves would be more effective at finding bugs. But what they found was, and what they were hoping to find, which was great, was that using an AI agent and kind of observing it actually made the testers more efficient at finding bugs. They found a higher percentage of the bugs overall. It took them less time. Truth is, as humans, we're just kind of terrible at multitasking. You can't be playing a game and trying to take notes on it and expect that you'll get 100% precision and recall on all the bugs that are present in that game, especially under time pressure. As a human, you know, you're giving a lecture, you're trying to monitor the memes on Discord. You can't do both at once very efficiently. It's tragic, but it's true, which is why these kind of AI-assisted approaches can be really beneficial for quality control. So, looking at our second category, playability evaluation. Playability is trying to validate game content in the context of the game's rules. So, is this level possible to complete? If you have a platforming level and the player has a particular jump height, and you've, say, generated that level, or your designer just threw it together real quick, and there's a gap that's slightly too wide, are players going to be able to finish the level? No, it's impossible. You did a terrible job, great job. But AI can fortunately help us kind of identify these flaws and make sure that our designs are valid. And this is part of what I said Noah was alluding to when he mentioned kind of the combat system. You know, if players are dying too much and you want to tweak that level in the game, can you maybe kind of use AI to infer how you need to rebalance your mechanics to ensure a particular level of difficulty? And this is what these kind of approaches want to kind of look at as well. Are certain items maybe unbalanced or broken? You know, will players be dying a lot more than you thought they would? Will players be employing a strategy that you didn't anticipate? This can be useful for quickly checking your designs. You can use this to check procedurally generated content as well. So if you're developing, you know, something like a Terraria or a Starbound and you want to make sure your level can be navigated, this is the kind of approach you can use as well, rather than relying on human testers and seeing, you know, is the level easy to complete by a human player. And while this does kind of border on quality control in a way, you can see that there's ways to tweak these agents to maybe mimic your average user performance rather than your ideal user performance. And then it turns into kind of finding out whether the level is playable for the average user rather than whether it's just possible and has no bugs in it, which is what quality control is generally concerned with. So you can integrate this into a sort of design and evaluation loop where you think of AI again as an assistant or a collaborator rather than just a replacement or an underling for human labor. And a couple of systems that have done this, these have both had papers published about them as well, so feel free to look these up on Google Scholar, are Tanagra and Rapossum. So Tanagra is a kind of AI-assisted level designer for platforms. And what it does is it breaks levels down into a sequence. So at a high level, looking at some of that same sequence recognition tech you'd be looking at for recognizing player goals, completely different context. Here, instead, you're using those sequences to kind of construct a level that has an appropriate amount of challenges versus kind of long segments versus enemies versus et cetera, et cetera. So the way that Tanagra kind of applies playability evaluation to this is as it's either generating levels or looking at levels generated by a human designer, it will automatically kind of use a pathfinding agent in the background to determine whether those levels are playable. And the reason why this is helpful is as a designer, if you're making a level and you accidentally place something maybe too far apart, maybe you have your enemies structured in such a way that players aren't going to be able to make it over a jump, the program can immediately give you feedback on that, say flag your level saying this part of the level is impossible. And this particular system also kind of has an automated option that you can use where the AI will kind of auto-correct your level design as you go to make sure that the content is possible. It also has kind of a mode where it can generate levels entirely on its own. The authors of this paper kind of did a really cool job of mapping out the space of possible levels that could be generated and kind of critiquing almost the artistic availability of the AI. Really cool for someone, anyone interested in procedural generation. Rapossum was another tool with kind of a similar application. This one used for cut the rope levels to be generated. And what they did here was they kind of had a rule-based agent, so one of those more classical expert systems that would basically be aware of all the rules of the game, take every possible action, every step in an intelligent way so that it wasn't going through literally every possible action, which just kind of blows up the possibility space. And then after a human designer puts in a level, this would kind of automatically tell you whether it was playable or not, how many steps the optimal strategy is, giving you feedback on the difficulty and the like. And this obviously also was paired with kind of a procedural generation tool for the levels as well, kind of AI as being either an assistant or a critic to a human designer, but also to an automated designer for procedural generation of content. Another interesting one, recycled cardstock, is kind of, researchers love giving names that they think are snappy and clever to their frameworks, but pay no attention to that. This one in particular was for testing card games. So based on a configuration of either having players that took random actions or players that had what's called a forward model of the game, basically kind of projecting what could happen at each stage, all the possible actions, and then picking the path that led to the greatest possible score for that player. That's something you guys will be learning about in AI next year as well. They use this to kind of evaluate a game's design. Things like finding out whether the order of turns has a significant impact on players, whether there's a dominant strategy, and so on. So basically using it to evaluate the balance of a game rather than the playability of a game. You know that a card game is possible, but are there maybe strategies that you haven't seen before? So lastly, kind of the most interesting category, to my mind at least, playtesting for UX with AI agents. Sounds kind of crazy. Human players are complicated. We have emotions. We have different strategies. How can we look at replicating this with AI and figure out just what we're doing and what we're thinking as humans when we play a game? This is especially challenging just because we're trying to make the agents flawed like people, but also playing well like people. It's really difficult to strike that balance and to kind of try and imitate the complex library of behaviors that real humans exhibit. There's a lot of different applications for this. One is just finding agents that kind of mimic your target player. So as I said before, you know, if you're finding it really difficult to recruit, say, kids or people that are really skilled in a particular MMO, can you kind of mimic the behavioral traits that you'd expect from that? You know, do kids have shorter reaction times? Do they maybe have less experience with a particular genre? Is your really skilled MMO player going to have a slight kind of bonus to their combat initially simply because they're really familiar with the nature of the game? Can you maybe create AI agents that mimic those characteristics so that you can have players that are more representative of your target audience rather than relying on kind of a subsample that doesn't really reflect who you expect to play your game in the wild, as it were? And the ultimate goal here is obviously to partially automate the user testing process, to kind of enable developers to test earlier, for it to be cheaper, for it not to take as long, and so on. And this is what my research is concerned with as well, which I'll give you a preview of in a second. Obligatory academic shameless self-promotion. But the application of this is basically to kind of critique designs early on, fixing glaring issues before you move on to kind of that polished testing at the end, where you then do tests with actual humans. Another place where this is kind of applicable is developing in-game AI. So if you're trying to make AI that's more convincing, that's more realistic, learning to imitate the action patterns of real players is also really valuable for that. So this is just another example of how games user research can kind of drive more development and innovation in game design as well. So my research, this is really difficult to see on the projector. I guess you guys will be able to see it in the slides, hopefully. There's a couple screenshots there. Is concerned with trying to imitate human navigational behavior in games. So if you drop a person in a virtual world based on whether they're more of an explorational player type, whether they really like combat, maybe how experienced they are, they're going to take a different path through that world. If you have a lane that's riddled with collectibles and a lane that's riddled with enemies, someone who maybe has a little less experience and isn't super confident, is really cautious, is going to take the lane riddled with collectibles. Someone who's maybe more of an aggressive or dominant player type is going to take the lane riddled with enemies. And kind of the problem that we're looking at is saying, you know, based on kind of your target audience, the type of players that you want to be engaging with your content, are players going to be getting lost? Or are they going to be missing out on anything based on the way your levels are designed? If you take a bunch of inexperienced players and you put them in a really labyrinthian level with a lot of enemies and a lot of different optional goals, and then an exit door that's really easy to reach, are they going to miss a lot of that optional content just because they don't feel confident exploring with the way the world's laid out? And those are the types of questions that we're really trying to answer. Another example of past research that has done something kind of similar is called procedural personas. You can also find this on Google Scholar. The author is Christopher Holmgard. He works at Unity. He's done some interesting work with this. Basically looking at taking a 2D adventure game and kind of learning the patterns in actions that different players display. So they used a combination of reinforcement learning, I mentioned before, and evolutionary algorithms, which is basically making a bunch of machine learning agents, taking the ones that do really well, mixing up their parameters, and then making a new population from those agents. Yes, it's exactly what it sounds like. And over time, using that approach, you can essentially create these agents that get better and better and better at the intended task. So the personas that they made for this dungeon game, they had things like aggressive, that would be monster killers trying to kill absolutely every enemy in the level. You'd have your treasure collectors that went straight for the achievements, straight for the rewards, ignored combat, ignored actually trying to get out of the level until they collected everything. And they found that in evaluating this, they could actually pretty reliably reproduce the moment-to-moment decisions made by a human player. So even though this was a really simple case study with a simple game design, just kind of really interesting proof of concept for how you might actually use an AI agent to mimic the behavior of a real bona fide human player. Another tactic that's used is imitation learning. I'm so sorry the projector is so dark. Screenshot there is from Forza Horizons. So Microsoft actually implemented this in a couple of the Forza games. What imitation learning is when your ground truth data set that you're trying to get your machine learning algorithm to essentially replicate as its output is data from some actual real player. Obviously, this isn't true in all fields. If you're looking at something like robotics, imitation learning might be used to get drones to learn from one another, or for a robot to kind of learn from how a human navigates. But in the context of games, imitation learning is when you essentially have some expert player and you try and get a machine learning algorithm to reproduce that player's behavior. And then, after the algorithms learn to reproduce the player's behavior, you take that machine learning agent and place it into a new situation, the thinking being that it will essentially behave like that same player would in that new situation, despite never having been exposed to it before. So if you guys have heard of the drivatars in Forza, this is actually how they work. So profiles built up of a particular player's kind of driving or racing style use imitation learning to learn to reproduce their driving patterns. And then when that's applied to a new set of circumstances with a new set of opponents around you on a different map, they drive in the same way that that player would. So when you're racing against someone's drivatar, it feels a lot more like you're playing against that player rather than just an AI that's objectively learned how to drive around the track really efficiently. The idea being that this is a lot more interesting for players to compete against because it really reproduces more of that human experience rather than just feeling like you're playing against a machine. So if we're looking back at kind of bringing this all together, what does this mean? Where is the field going? We can look at some of the challenges associated with this. And to me, the biggest challenge is kind of how do we evaluate these tools? You know, if you've never had a player, going back to the drivatars example, since it's still fresh, if you've never had that same player go through that same map with those same opponents, how can you validate that you've created an AI that actually behaves as they would? Perhaps, maybe even more importantly, how do you avoid punishing a system that's actually doing really well? If you take that same player and you have them play through that same set of circumstances, but maybe it's a different day, maybe they feel slightly differently, maybe on one day they would behave more like the AI and maybe on another they wouldn't. How do you avoid penalizing that system? How do you know when you've gone far enough? Now, there's a few different ways you can evaluate AI systems. There's some obvious objective metrics. So before we try and tackle that question, things like computational performance. Is the algorithm reasonable to run on your computer? If you're using it for data analysis and it takes an hour to extract emotion data from 1 second of video, you know what? Maybe that's not feasible for you as an indie developer. Accuracy. This can be really straightforward for certain systems. If you have a facial recognition system and you have a set of images that are labeled with the ground truth expressions, you can evaluate accuracy really easily. But how do you measure this for player-like agents? Going back to that example. How do you know your algorithm is human-like? There's a couple different approaches you can do for this. You can compare... Gabby, yes?
Facial coding.
Yes, exactly. You can compare gameplay to human traces. So you can take a coding approach where you basically go back to a human's play trace and you say, okay, at this point, this decision was made. You know, the player turned left, they killed this enemy. You break down their actions atomically. And one of the cool things about testing an AI agent is that for this, you can essentially reconstruct the exact game state at the moment a player made a decision, put your AI in there, and see what it does. And this avoids the idea of error propagation. So if your AI turns right, you know, suddenly you're going, well, okay, that's it. They can't possibly make any of the decisions that the player made after turning left. My system must be terrible. No, instead you say, you know what? At that decision, the AI chose differently. If you reconstruct the game state at the point of the next decision and the AI then kills the same enemy and plays the rest of the game exactly the same as your human player, your system's actually pretty good. Maybe just made a slightly different decision at the beginning, but ultimately still replicates that decision-making process effectively. So those are kind of a broad overview of the approaches you can take for looking at accuracy. There's actually been some work done on how to evaluate, in particular, human-like agents. There was, I should say, a competition run by a professor from Scandinavia called Julian Tegelius, who does a lot of work in this space, on an AI for a clone of Super Mario Brothers. They had a lot of different tracks in the competition, some to see, you know, what could play the game the fastest. One year they had one to see whether they could create an AI that was really human-like, and then kind of had human juries evaluate it. So even something like just, you know, feeding footage of a testing AI playing a game to a human and saying, do you think it's a human or a robot playing? And this is basically the Turing test. It's something really simple, but it's something that's explored in the literature as well. And if any of you are interested in this kind of thing, it's a method you're going to want to look into. Another thing that maybe gets pushed to the wayside sometimes is the usability of the tool. So as a user researcher, is it actually useful for you? Can you use the interface? Do the agents do something that provides information that's helpful to you? This is ultimately, since your target audience when you're developing tools like this is user researchers, something you really want to consider. And also, is there a benefit to user performance? Going back to a system like Cicero, when I mentioned earlier, can you basically have a researcher use this tool and see if it improves their ability to make insights, you know, how quickly they can analyze data, how many issues they find. Is there a tangible benefit to the system being used? And these are some of the questions that you can ask when you're kind of developing these tools, when maybe as a user researcher, you're trying to assess whether one of these tools is right for you or whether it's just kind of a bunch of buzzword hoopla that's still way better for a huge commercial organization that has the resources to employ it. So this here is just footage from one of the Super Mario competitions that I thought anyway, the agent that ended up winning, I think this is the inaugural year, just using a star. I've actually heard Julian give a couple of talks about this particular competition, and the organizers were honestly kind of just throwing their hands up in the air for the fact that this agent won the competition because a star is such an old algorithm. But the lesson there is basically if you want to use the right tool for the job. And there are a lot of people that but the agent that actually ended up doing the best was just using a star. So even when you're developing you might be using something really kind of novel, really cutting edge, but ultimately sometimes it's just better to stick with what you know and with what you know. It's impressive, right? It's really, really simple. So, looking at some of the future work, kind of where the field is going. What are the frontiers of artificial intelligence in games user research? Well, the holy grail right now, much like the holy grail of AI that I mentioned earlier to have something truly general, is general video game AI and kind of game agnostic agents. So basically, rather than just having an agent that's really good at platforming games, can you have an agent that's great at platforming games and arcade games and RPGs and shooters and racing games, you know, like a human that had been playing games their whole life? This is kind of the grail for multiple reasons. Obviously, if we had an agent like this, it would make the idea of automating user testing and tweaking it to work with different types of games much easier. But also just the fact that games have been used as test beds for AI for a long time, tying back to the field in general. This kind of AI would also be really useful in robotics and broader AI in general. Imagine you have an AI that's gotten really good at playing racing games, just learning from pixels and actually getting the same visual input that a person does in a driving simulation. Where might that be useful? Perhaps autonomous vehicles, I don't know. This is one of those fields where the kind of crossover between game dev being thought of as a pure entertainment field and game dev maybe finding some insights or research results that are useful to the broader scientific community is actually an area of a lot of promise. We're not there yet, obviously. We're working on it. It seems like every few months now there's a new story about a new kind of deep learning network that's either really great at Dota or really great at some classical board game. We've kind of mastered Go at this point in the past couple of years, which is awesome. Integration with computer vision. So this is what I mentioned when I said playing from pixels. When you take kind of the same visual input that a person is getting, essentially instead of putting your AI into your code so that it knows what's going on in the game, actually requiring it to process the visual input that a player would get, and then based on that, you know, make decisions about gameplay, actually pass back raw controller input as opposed to walking around in a model of the game. More sophisticated player models. So looking at things like modeling what motivates people instead of just looking at patterns of action. You know, can we determine maybe a player's psychological profile based on the actions they're taking in games? And can we use that to learn even more about our target markets? Can we replicate human ingenuity and stupidity by using those player models to kind of then drive agents to test our games? So, in conclusion, I know it's a lot to think about. Hopefully, any of you interested in AI in particular found this interesting in some way. AI can basically help us address a lot of common challenges in GUR. That's what I want you guys to take away from this, that AI isn't just about, you know, creating opponents for players in games, that you can think of AI more broadly as being a tool that's applicable to a lot of different areas of games user research. It can help you analyze your data. It can maybe even help you as a tester. And it can help you with things like improving efficiency, maybe representing your target market more effectively in playtesting, working with unmanageable data sets. And they can really help with or assist you in parts of the pipeline. It can make it cheaper and easier for you, especially as an independent developer or maybe a freelance user researcher, to do the work that once would only have been accessible to a huge team of 40 people working at a AAA company. Techniques share applications between design and evaluation. If you're developing an AI to play your game for testing, it might also really help you to develop better in-game AI that's maybe more challenging or interesting for your players to combat against. And obviously, this is just something that's of interest to kind of everyone that works in games. I think this is really something that either as a developer or a user researcher, you really want to consider, because even though everyone loves to use AI and machine learning as a buzzword these days, the truth is, even though the impacts might be overblown in a lot of different domains, I think in games user research, it's one of those where it's kind of just starting to come out of the woodwork. And if it's something you're interested in, it's definitely worth looking into. So, does anybody have any questions about the lecture, about assignment 2?
Can we go on there to ask you questions?
Yes, of course, of course. I'm going to, since Jason rescheduled his presentation, I'm going to be dedicating kind of the rest of this 15 minutes or so. Come up to me, ask questions about the assignment, ask questions about the lecture. Other than that, no activity today. Don't stress. Good luck with your assignments, and have a great week.